Welcome everybody to Rigaku's seminar on light element analysis with wavelengths dispersive XRF to reliably quantify elements like boron and fluorine. Before we start, maybe let me introduce myself. My name is Niels Heppe. I'm a application specialist here at Rigaku Europe, and today's presenter will be Carmen Kaiser Bergmann, who is an analytical chemist for over 20 years, working with XRF and the cement industry in South Africa for many years, and is now here since 6 years application specialist for the region of Europe, Middle East, and Africa. Yeah, and before I hand over to Carmen to start her presentation, let me first start with some general things for the Q&A session in the end. Please use the Q&A function of the Zoom software. We will pick a few questions to discuss afterwards, and when there are more questions, we will come back to everybody and answer their questions by email. The recordings of the webinar will be made available afterwards. The processing will take a bit time, but you will notified when the recording is ready to be rewatched. And in the end, we will send you a little survey to improve our webinars and get some feedback from you. And we would greatly appreciate if you take the time to fill out this survey. Yeah, and with this, I would hand over to Carmen and
thank you so much, Niels. We will talk later.
Yeah,
thanks. Welcome, everybody. And as an overview to the presentation or the webinar that I will do today, I will try to share with you some application examples. So before we start, maybe it's nice for you to know a little bit about wavelength dispersive XRF, and basically some of the best practices that are employed when preparing samples either as a pressed powder or a fusion. And I would like to share some examples of Fluorspar, so the analysis of fluorine in Fluorspar, which is a mineral, and the analysis of boron in tourmaline. So given these two kinds of examples, the traditional ways of preparing samples as pressed or fusion, I would also like to share with you further applications for the determination of fluorine and boron, which might be quite interesting for you. And of course, what are the unique features and benefits that we can offer in terms of our equipment to get the best results for fluorine and boron specifically. And we will conclude with a summary. Oh, and of course, question and answer. Okay, so let's look at a brief introduction of X-ray fluorescence. So here you can see X-ray fluorescence is basically an analytical technique where we can do the total elemental analysis, either qualitatively or semi-quantitatively, and even with calibration methods, so quantitatively. So you can see here a depiction of a spectrometer, which consists of an X-ray tube with a sample that we will bombard with primary X-rays. And as you can see from the specimen, we would get a fluorescent X-ray, which would then be collimated through a collimator or a slit in this case, onto an analyzing crystal. And of course, this analyzing crystal then gives rise to a unique characteristic 2θ angle based on the Bragg equation to give you a specific chromium or iron or nickel analytical line. So here you can see the energy of the line and the X-ray intensity. So if we do semi-quantitative analysis, we use the peak heights and the fundamental parameters part to estimate the composition. But if we want to, for example, look at a quantitative method, we would check the peak height as well and peak angle, and we would calibrate with known standards, and then we would be able to determine a precise quantification of that particular element. So let's talk a little bit about a pressed powder. So if we use a calibration method, we need a calibration with calibration standards. And because XRF is a relative method, we need to match the standards and the unknowns very much the same. Yeah. So when we prepare a pressed powder sample, we aim to get the highest intensities, and the only way we can achieve this is if we reduce a particle size effectively. So if you look at the top diagram, we can see a pressed powder, but we have very large grain sizes and not a very even distribution of the particles. And so therefore we would not get a desirable signal, and we would get much lower intensity. So the aim with a pressed powder is to have small grain sizes so that we get higher intensities, and we get homogeneity within the material by reducing particle size. And we want to make a compact specimen, so we have a defined density, because the higher we have a pressure, the higher the intensities are. So here you can see a very nice example of many pressed powders, but you can see that the analytical surface is smooth, flat, and evenly distributed, and we have an infinitely thick sample. So that's another point that we have to consider. Yeah, so particle size and infinitely thick. So if we look at this diagram, the aim with a pressed powder is to get maximum intensity. So, of course, if you have larger grain sizes, we would get lower intensities. Smaller grain sizes, we would get the maximum intensity. So this is what we want, yes? And also we need to take care, especially if we want to measure light elements, because the light elements are read from the top micron layer. So we want to have this finely divided material so that we get a consistent signal for the determination of, for example, fluorine or boron. Yes. What other impacts do we have from a pressed powder? So if you look at this diagram here, you can see two calibration curves. And if you have a pressed powder calibration, the matrix and the mineralogy play a big role here. So if calcium exists as a calcium hydroxide or a calcium carbonate or a calcium fluoride, you would get different groups of this calcium. And therefore, it's really important in XRF, if you have a pressed powder method, that we have matrix matching calibration curves. Yeah. If we go for a fused bead, we take away this matrix problem, and we would get all the minerals and all the calcium on one calibration curve. So basically, you need to consider these two aspects, yes? So in short, pressed powder needs matrix matching and mineralogical matching standards to be able to get a decent calibration. And fusion, we take away this matrix and we solve this issue, yeah? But we have a lot of dilution here, and we also may get rid of some volatile elements, yeah? Okay, so if we look at all the spectrometers that we have, the focus today will be on the Primus IV, because I've used the Primus IV, which is our standard system, designed for high throughput of samples. And I will talk a little bit more, but one of the biggest benefits here is, of course, many of the hardware and software features that we have here to basically measure the pressed powders or the fusions for the analysis, the elemental analysis. Yeah. Okay, so let's talk a little bit about light elements and a little bit about the theory. So here we can see an example of the fluorescent yield of some of the elements that are present in a sample. And today we want to focus on things like fluorine and boron. So unfortunately, fluorine and boron are light elements and the fluorescent yield is very small. So therefore, we try to aim to get the maximum sensitivity from these elements. Yeah. So in the next few slides, I will show you how we can achieve maximum sensitivity, because in XRF we have this very low fluorescent yield. Another problem that we have with fluorine is if your sample contains a lot of iron or manganese, we could have a possible overlap. So I will also show these matrix corrections that are possible to eliminate this overlap problem or absorption or enhancement problems. Yes. Okay, so if we look at the mineral fluorspar, it contains a lot of fluorine, of course, and fluorine is an essential element for example, for the production of Teflon. And it is also used in the electronics industry, particularly in semiconductor manufacturing. Fluorine can also be added to the toothpaste and drinking water to prevent tooth decay. Yeah. So it's quite an essential element, yes. So we need to, of course, quantify fluorine properly in such kind of materials, be it from the original ore, like the fluorspar, to semiconductors and so on, yes. So traditionally, in the old days, or even now, today, we do the determination of fluorine using the ion selective electrode method. So here we have an example of how tedious this kind of measurement is, because here you can see that sample preparation and extraction is extremely time consuming. You would need to set up your calibration standards, add the ionic strength adjusting buffers, and set up a calibration that looks something like this. And of course, once you've done the calibration of the ion selective electrode, we would then, of course, also need to prepare the samples in the same way. We also have some problems with this kind of technique, because we have interferences from alumina and iron, and so the ionic strength adjusting buffer is really needed for this. Yes, the advantage, of course, with the wet chemistry technique is, of course, we could get down to very, very low levels with this method. But of course, if this is not needed, then of course we can use something easy like XRF. Yeah. So the benefit with XRF is that, of course, we have much easier sample preparation. And once we have a calibration, it's not really necessary for you at all to basically recalibrate this method, because we have the biggest advantage here of having what we call check samples and drift correction procedures that help us to maintain these calibrations. So the analysis of fluorine becomes far more easier and far more achievable in a laboratory environment. Yeah. So let's look once again at how we prepare the pressed powder sample. So of course, it's really important for us to always dry our material. Of course, get a representative sample, yes, but this is not about that. We would dry the representative sample, and hopefully it's large enough to be able to represent what we are trying to determine. Of course, undergoing techniques like splitting and milling. So we have different ways of milling the sample. So if it's a large sample, we would reduce it until we have the final step, which is the final milling step, yeah, where we need to achieve a particle size for XRF of less than 45 micron. And of course, pressing the powder. So here you can see some examples of binders and how we would press the powder. Yes, one of the biggest advantages here is to use something like this, what we call a spectra blend. And the spectra blend has the biggest advantage of helping to ensure homogeneity and to reduce particle size effectively. Because as you heard from the previous slides, in theory, if we want to measure fluorine in a pressed powder, it's measured from the top micron layer. And so therefore, reduction of particle size is extremely important. So we want 98% of our particles to pass 45 micron. Yeah, so the problem is most powdered substances are multi-phased or compositionally complex, and they comprise of individual particles and crystal phases with different hardnesses, different densities, different configurations. So each particle that is present behaves in a separate entity. And so this spectra blend helps to reduce this and form a homogeneous blend for XRF analysis. So once we've reduced particle size and we start to press the sample with the spectra blend, the powdered sample then transforms into like a plastic or plasticized pellet, which will produce a very smooth analytical surface with no blemishes, no scratches, and that the surface is resistant to chipping or flaking. So this is very important for XRF. So we can also keep the integrity of the sample later on by storing it in a desiccator, for example. Okay, what about a fusion method? Yes, we can also use fusion for fluorine. And a lot of you would say, but how? Because we subject the material to very high temperatures. Yes, but we can introduce what we call a lid. Yeah, and if you look at the system that we use here, this fusion system, it's an enclosed area where the fusion takes place in an enclosed place with a lid. So therefore, we do not lose any of the fluorine. And of course, if we want to increase sensitivity, instead of taking the traditional 1:10 ratio, we could take a 1:2 ratio. So increasing sample weight, to get a more concentrated fluorine signal from our fuse bead. So in the next few slides, I will show you that. So how else can we increase the sensitivity? So not only with pressed powder or fusion, but also with what we have available in our spectrometer, so the hardware part. So if you look at Rigaku, we have two kinds of crystals for the determination of fluorine. One is the RX26, which is a synthetically made Rigaku crystal, which has a certain D-spacing. And we also have an RX35 crystal. So if you look at the information here at the peaks for this particular sample, you can see that if you use the RX35 crystal, we increase the sensitivity a lot, and we get a much higher intensity. So here you can see on the RX35 crystal, we get 1 kilocount, and here we get 0.2. Yeah, so it means that we increase the signal considerably by just changing, for example, a crystal. Here we have an example of a polymer sample using the RX35 crystal, and this polymer sample contained 50 ppm of fluorine, so very light matrix, but we can get a very decent signal with this kind of crystal. So really, really nice for method development, where we can define a proper peak angle and a proper background. Yeah, and then of course we can decide further with our software if we would like to, for example, do, instead of a continuous scan, something like a step scan. But this is just an example. Okay, so let's look at the calibration of fluorine in Fluorspar, but using the fusion method. So I already described the fusion method, and very briefly, I've just shown it here, what kind of flux that we used. So in this case, we used a flux of mixture flux, which is far more conducive to dissolving the sample in this glass matrix or fusion matrix, yes? So the mixture flux shown here, the non-wetting agent that we used, and the amount or the ratio of sample or standard to flux. So here I've given you a summary of what kind of certified reference materials we used. So these are all, from here onwards, we have certified reference materials, and these are in-house secondary standards. So it's always good to have a combination of secondary and certified standards, yes? Here I showed you the example of the size of the beads. So, of course, in our software, it's very easy to create calibrations because we just follow the nice calibration tree, and we work step by step. But what I wanted to show you here is that, of course, it's also possible for us to include calculations in the software. So, of course, if you're wanting to measure fluorspar, fluorine and fluorspar, you probably would also, if you don't have a diffractogram, you could then also calculate the calcium fluoride by including some kind of calculation. So it's also possible to do this in our software very easily, and it would be reported with the final result. Here I try to show you the example or calibration summary for this particular fluorspar and the elements and the oxides that were done. So, of course, the first thing that we would like to look at is, of course, the regression, the goodness of fit, and they're all linear fit, and, of course, the kind of detection limits and the kind of accuracy that can be achieved with this kind of method. So, of course, the focus today is on fluorine. So, of course, here I tried to show you what kind of calibration we could get with fluorine using this method. And, of course, showing you basically with this goodness of fit that we have shown with the regression correlation, what kind of standard and calculated values we get from the slope and intercept that we have here. So very good agreement and a very small deviation from the standard and calculated values, yes? And a decent signal, of course. So in the next slide, I try to show you how we can calculate the sensitivity fluorine, okay? And basically, here you can see the equation that we used. So the sensitivity of the spectrometer for that particular element is calculated by taking the number of detected X-ray photons that we get and dividing it really by the measurement time that we have taken, multiplied by that particular concentration of that element. So here are the parameters that were used and the counts that we got. And here you can see the defined sensitivity. Yeah. So this is always important for us to know as an analytical chemist. Yeah. Of course, in the next few slides, I just wanted to show you what kind of software features we have. So we can have what we call mathematical corrections or even ratio models. So the mathematical corrections that we have are divided into matrix corrections. So we can have theoretical alpha corrections, and we can have line overlap corrections. So these are the classical ones that we can use in XRF. And most importantly, if you want to measure trace elements, for example, I think in some of the previous webinars I've shown you that we can also use a ratio method. So if you have a pressed powder method, we can even implement what we call the scattering X-ray correction method. So here we have introduction of the matrix of the sample by measuring the scattered X-ray from that particular standard. Yeah, and here we would use the Compton line. So, for example, if you have the rhodium tube, you would measure the rhodium K-alpha Compton line, and this would be a matrix correction. Very effective Compton scattering ratio method for trace elements in mineralogical samples. Yeah. So our matrix correction, theoretical alpha correction models that we use in our software are divided into the 3 different models. the mathematical models, so the Chance-Trail, de Jong, and the JIS model. Yeah. Here we have the example of how easy it is to apply this kind of correction in our software. So, of course, if you have the calibration, we can click on the correction button, and then we can apply what we call a theoretical alpha calculation. And of course, we can choose the best model that we would like to use. Here we have another example of a correction model, but in this case, we are applying what we call absorption or enhancement correction. So also very easy to navigate your way in our software. Here's a far more complex subject where we have an overlap. And of course, if you have an overlap, and in this example, we have sulfur and molybdenum with a very strong overlap, then of course we would like to measure the amount of molybdenum that is enhancing our signal for sulfur. But in our software, it's quite easy because then we can apply the molybdenum overlap correction. And here you can see in the calibration how we applied this mathematical correction. Yeah. So let's talk a little bit about how effective this ratio, the quantitative scattering ratio correction model is. So here you can see that if we measure the rhodium K alpha Compton line, we can improve the accuracy because originally the calibration plot would look like a starry night, which is very much what happens with pressed powders. And the only way to improve this is to do what we call this matrix correction, and it's called this ratio correction model. So, of course, each and every standard is measured for its Compton line. And of course, because of this ratio, we have improved the goodness of fit. And of course, we've improved the accuracy. Yeah, so very effective. Yes. And here you can see the example of the different types of matrices. So, of course, the lightest one here being grass. So it has a massive Compton line in comparison to the others. Yeah. Okay, so of course now I've showed you a little bit about the calibration, and of course I wanted to share some examples of the results. So this is an unknown sample, which is maybe not so interesting for you, but I think what's interesting for you is to look at a certified standard. So of course, here we have the example of a Fluorspar certified reference material, and we have a certificate of analysis showing the exact composition of the Fluorspar. Yes. So if we try to measure this certified standard by showing you repeatability with loading and unloading, you can immediately see what kind of standard deviation for repeatability we can get for major and minor and trace elements that are present here. Yeah. So of course, as you know, XRF is a very stable method, and we are very easily able to achieve these very good standard deviations for repeatability. Yes. Here's some more examples because we have more than just fluorine. And of course, we've also included some calculations here. But of course, we would like to compare these average results with a certificate of analysis. So this table shows you what kind of results we can expect at the 95% confidence level. So meaning if we have this method that I've shown you, on average, we could get 48% of fluorine with a plus or minus of 0.44% at the 95% confidence level. And we can then compare it to the certificate of analysis, which is shown here as the true value. So as you can see, for fluorine, we can achieve extremely good results for Fluorspar. Yes? Okay, well, what about tourmaline? So this is another kind of ore, yeah, and it contains essentially boron. And boron is extremely important element because it's really important for plant growth, and it can be used in fertilizers because, of course, it's important for the plant life. And and it also finds its way into glass. So in the glass industry, we use it as well, renewable energy materials, and even some of our cleaning products. So the unique properties of boron are very valuable also in the production of semiconductors and also in alloys. Yeah. So of course, we also need to quantify boron very easily. So of course, boron by wet chemistry is very tedious. So there's many ways to determine boron. We can use ultraviolet spectroscopy. We can also use titration methods, ICP, OES, ICP-MS, and of course, even atomic absorption with graphite furnace. But also we have some challenges with these techniques because we have interferences and so on. But most of all, sample preparation and extraction is quite tedious and time consuming. So if you're in a quality control production area, it's not so easy to try to implement these kind of techniques in this kind of environment. So, XRF is once again quite a nice benefit to have in an XRF lab to be able to do boron, yeah, because once again we have the much better or much easier way of sample preparation, and we don't have to worry too much about always doing daily calibrations. So once again, we can maintain the calibrations with what we call check samples, and of course, maintaining it with what we call a drift correction process. Yeah. Okay, so boron has, of course, got a very low fluorescent yield, and really we need to take care how we are going to measure this with XRF. Yeah. So here we have the example of where boron can be added to glass to produce heat-resistant Pyrex glass or borosilicate glasses, which are commonly used in laboratories. Yes. Of course, some of our glass customers really use XRF to measure the boron in their final products and, of course, their raw materials. Yes. So once again, just explaining how important sample preparation is in terms of pressed powder. So aim always with XRF homogeneity and, of course, particle size. Yeah. So less than 45 micron, because once again, boron is a light element, and because it's a light element, it's read from the top analytical surface. Yeah, so some of the tools and binders that can be used to prepare the pellet. Yeah. Okay, so another example here is to show you how we can use alternative applications for determination of fluorine and boron. In liquid samples. So very often we have liquid samples, and of course we have these very nice filters, which are called microcarry, ultracarry, and it's possible for us to increase our measurement for this liquid sample using the filter to boron and fluorine. Because if you use the traditional liquid method, cup method in XRF, the film that we use can absorb these two elements. So boron and fluorine will be absorbed by the film. So if we use this kind of filter method, then of course we can very easily measure boron and fluorine. So of course, the idea for sample preparation is relatively easy because of course we can place a dedicated amount of the liquid, standard or unknown, onto the filter, dry the filter at a desirable temperature where we do not drive off the fluorine or boron, and land up with a specimen that can be measured in vacuum. So this also increases our sensitivity. So the possibility to have a pre-concentration onto this area that you see here, and of course measuring in vacuum. Yeah, but of course if we want to try to measure this very thin filter, we need to use special assembly for the cup, and here you can see the assembly, which consists of a sample cup but with a backscattering cup. And we would merely place the filter on top, and the backscatter cup is consisting of alumina to eliminate any scattered X-rays that we could get from the cup. And in so doing, we also measure only the portion where the liquid is, so the 20 millimeter diameter. And yes, what kind of measurements could we get? So, of course, once again, creating calibrations for boron and fluorine is relatively easy with the filter method, because we could use AA standards or ICP standards and create the range. So here you have the range from 0 to 500 ppm and 0 to 50 ppm for fluorine. And of course, here you can see the calibration graphs for those ranges, together with the measurement parameters that we used. So in both cases, we used two different kinds of crystals. So boron, we have the dedicated RX85 crystal. And for fluorine, in this particular example, I showed with the RX26, and both of them using the flow proportional detector, showing you what kind of excitation conditions we use for the K-alpha lines, and of course the collimator. So of course with the collimator for boron, we want to use a special kind so that we can get a good signal. Yeah. So once we have created this calibration, we can then of course measure our water samples in the same way, the same preparation. And of course, here you can see some examples of the boron. We measured it, we created the measurements 3 times. And you can see on average what the result would be for boron and fluorine in this particular water sample. So what's interesting for us to always look at is the kind of standard deviation that we would get. So on a boron, we could get 11 ppm standard deviation, and fluorine a 2 ppm deviation, yeah, standard deviation, yes. So showing you how easy it is to measure boron and fluorine at a low concentration level in water. So it's possible, yes. Let's look at some of the unique features and benefits that we have on the Primus instrument. So here we have a very nice feature which is called automatic pressure control. So if we have a very stable and consistent vacuum level, we can get a very consistent signal. Yeah. So here you can see in the diagram that if we use the automatic pressure control on our system in the software, we will get a very stable signal. If we don't have the vacuum stability, we could get a rise in the boron content. So the benefit, of course, with our system is to use automatic pressure control for a light element like boron, because we will achieve more consistent, stable results. And of course, from this diagram here, you can see if we measure a boron K-alpha line and we have, for example, a 5 Pascal change of in the vacuum level, it can result almost in a 2% intensity difference. So it means having this function in our software is a big advantage. Yeah. So if we look at our X-ray tube, it consists of rhodium anode, so it's a 4 kilowatt tube. But the important thing for you to note is that we have a very thin beryllium window here. And the beryllium window thickness is 30 micron. So it means, especially for light elements like fluorine and boron, which is what it is about today, we can get a 40% increase in intensity for these low fluorescing elements like boron and fluorine. So the benefit, of course, is that you get a better sensitivity for these elements, yeah? And of course, because of this better sensitivity, we can also reduce analysis time, yeah? And most importantly, because of this increase in sensitivity, we get much better limits of detection. Yes? Okay, so the other benefit is to use our special crystal, which is the RX85 crystal. And in most suppliers, we would get a much lower intensity, but with the RX85 crystal, we increase the sensitivity for an element like boron by at least 30%. Yes? Once again, leading to much better limits of detection. Yeah? Okay, so here we have an example of some measuring conditions for boron, because in the next few slides I will show you how to prepare the boron oxide in different matrices, so pressed powders and fusion, to show you the differences. Okay, so boron, the element boron, the K-alpha line, has a very, very long wavelength, making it sometimes very difficult. So these improved features in our spectrometer, like vacuum stabilization, better crystal, thinner beryllium window, gives you better sensitivity for this element. Yeah. Okay, so let's try to look at the differences in sensitivity between a 2.4 kilowatt versus a 4 kilowatt system. And the differences with the automatic pressure control. Yeah. So here we have an example of an experiment that I tried to show you by using different excitation conditions. So almost using 4 kilowatts of power, then 3, then 2.5, 1.8, and 1.2. What effect it will have on the intensity. So here you can see the intensity for these different excitation conditions for the boron K-alpha line. So as you can see, I tried to put it in a sensitivity chart to show you exactly how we can increase the sensitivity by applying a maximum or a better excitation condition. So more excitation for this element, the higher the intensity, of course, and it's then possible to measure very, very low levels of boron. Yeah. Here's some examples of using boron in the pressed powder method. Yes, and showing you different calibrations. So here you can see some values of boron ranging from about 3% almost to 7%, and seeing what kind of intensities we can get with the conditions that I showed you before. Yes, so increasing the excitation condition, using the best crystal, and optimizing the best measuring time. Yes, so goodness of fit shown here with 0.99. And in this particular sample, we had a lot of alumina. So, of course, the alumina overlap correction has been applied to this particular calibration. What about boron in glass? So, of course, the boron is used in the glass manufacturing process to produce the borosilicate glass. And here you can see the example of the kind of calibration that can be achieved in glass. So it's very different to pressed powder matrix because the glass has a different matrix to the pressed powder. Yeah, because remember in the beginning I showed you the theory about the matrix of the sample is influenced by its mineralogy. So now in the glass form we've taken away this matrix. Yeah, so we've now got a neutral matrix. So therefore, our goodness of fit and intensities look quite different to what it is on a pressed powder. Yes. So, of course, with this calibration, we also tried to show you how we can measure certified reference materials. So in this case, we used the NIST standard, which are very famous standards, to show you what kind of repeatability we could get on the NIST standards. Yeah. And you can see that the standard deviation for repeatability on a major composition and a minor composition show very small variation in the results. Yeah. Of course, we can also measure an unknown sample, so without knowing the value, to show you what kind of precision we get. So this shows you, of course, the kind of accuracy that we can get, and this shows the kind of precision that we could get. Yes, showing you in more detail the NIST standard, and then calculating limits of quantification and limits of detection on that particular calibration. So it's very possible to create a boron in glass with a good range, but also showing what kind of accuracy can be achieved with this kind of range above. Yes? Okay, so let's look a little bit deeper into boron with different matrices. So here we have an example of the kind of spectra that we could get for a pressed powder, and the kind of background fitting that we would get. So, of course, because boron is a very light element, we will get a very wide peak, yes, with a nice background fitting. So our software also has the ability to apply this kind of nice background fitting. Here we have the example of a different matrix. So now we have a fused bead, and showing what kind of spectra we could get with, of course, it's still very wide, but a different kind of background because of the matrix. Yeah. Glass, also a slightly different matrix to the fusion because it's in a different form with maybe high silicates, for example, and calcium that's present. So, of course, because of its different matrix, once again, we have a defined background for this kind of matrix. Yes? So showing you in comparison what a pressed powder calibration and what a fused bead calibration would be. Always pressed powder relies on particle size, matrix, and of course fusion is much easier because we've taken away the matrix. Yes. Get that one. And lastly, the calibration that could be achieved for the glass with an overlap correction. Yes. So let's talk a little bit about the background correction. So of course here you can see, because this boron glass has a much higher dilution here, we have a very high background, but in our software, it's very easy for us to apply different kinds of background models. Yeah. So we can have 2 points, we can have 3, we can even have 4-point backgrounds. Yes. So in summary, XRF is quite a nice technique to determine boron, especially with our hardware and software features. So hardware being the crystal that we can have, so the RX85, the fact that we have a 30 micron beryllium window to increase the sensitivity, and of course the wonderful feature that we have, which is called the vacuum stabilization, so automatic pressure control, which allows us to achieve very stable and consistent results for a light element like boron. Yes. So our solution for Primus IV is very favorable, especially for pressed powder samples, because of course we have this industrial unit with an X-ray tube above the sample, and the fact that we have the X-ray tube above the sample ensures that we have a long-term stable intensity from here, because of course we don't have any problems with falling dust or any contamination or any reduction of intensity because of tube above. Of course, the calibrations, either pressed or fusion, can be very easily set up with a combination of certified or secondary standards. Yeah. What's important for you to know is that our software has the ability to include in any kind of application a way of checking the method. So we can introduce what we call check samples. And of course, we also have the drift correction procedure, which is also very nice to maintain the calibrations. So we also, as an application team, help our customers understand the best operating practices for XRF, and we train you very nicely on how to interpret these results for checks and drift corrections so that we have a long-term stable method with very consistent results. Yeah. So this is an example of an automatic, what we call standard operating practice, where we could automate your calibration maintenance for check samples, for drift corrections, and checking the stability of your instrument. Yes. So if you want to know more, please contact us. Yes. Of course, not only is the application side important, but also our strong service support center, and our service part is ensuring that you have a well-maintained spectrometer with extensive service contracts available to you to ensure that your instrument has no downtime. Yes? So, of course, why should you choose Rigaku? Well, we have the excellent XRF instruments for industry with, as you can see, a very good analytical performance. And of course, all our instruments are compliant, for example, with the international standards. So here are some examples. And most importantly, not only the instrument, the hardware, software part, but also the possibility of having the strong service and application support. Yes. Of course, I think some of you may not know Rigaku, but of course, Rigaku is a Japanese company. We are proudly Japanese, and we like to have a Kaizen philosophy, meaning we're permanently developing and we continuously follow this philosophy, to improve our product. So we've got a long history in XRF with excellent spectrometers. So in conclusion, the Primus IV, together with flexible application packages, can help you to ensure that you have a good working environment with an XRF to give you reliable and consistent results. And most importantly for you to know, of course, X-ray tube above ensures that you have less risk of damaging your X-ray tube or any breaking pellets that may cause any problems. So yes, please visit our European Center of Excellence. And I don't know if there are any questions, Niels, maybe.
Thank you, first of all, Carmen, for the very nice presentation. And yeah, there are a lot of questions.
Okay.
Maybe we start with a few quicker ones on sample preparation.
Yes.
So one question is if we can measure boron also as fused bead, or if there's a problem with the boron containing in the flux.
Yes. So I tried to show you that, of course, the best method for boron is using a pressed powder method. But of course, it's really important with the press powder method to have the correct preparation. So, of course, I tried to explain that we could introduce the spectra blend to help to minimize particle size and almost produce this flat, homogeneous analytical surface. So this is the best method. But of course, if we prepare this kind of sample with a fusion method, of course, our fusion flux contains boron. But of course, if we apply the fusion to our standards in our samples, realistically, it's always going to be the same amount of boron. So, yes, we can also use this kind of method, but it's always important if we have fusion that, of course, that we have the possibility of losing boron. So we need to be careful which kind of method that we choose. So to get reliable results, I would always rather recommend to rather just use the press powder method. But then we have to always ensure that we have the best possible particle size, mineralogical matching of standards. So this is my recommendation. Yeah.
Okay, thank you for the answer. Is it maybe the next question? Is it possible to measure the lighter elements like fluorine and boron in a heavy matrix like slags or steel making slags in the percentage range, let's say?
Yes, so if you have a heavy matrix, maybe even a metal sample or a slag or a ferroalloy, it's also possible to measure boron. Of course, we need to always try to choose the best sample preparation technique. So if it's a powder, ensuring the best practice for powder, for pressed powder. But if it's in a metal sample or a very heavy matrix like this, the important part here is it's solid already, but we need to ensure that our analytical surface is highly polished and very flat and smooth, because of course the signal of boron will be measured only from the very surface. So it's a surface analysis. So in fact, it's like from the top 20 micron layer. So it's always important to choose the correct preparation method, considering the type of material or sample that we would like to measure. Mm-hmm. Yeah.
Okay. Maybe a basic question. The question arises: what is a balance? You mentioned in your tables, and how can one determine this balance for different samples?
Yes, exactly. So in mineralogical samples, we sometimes have, the mineral form. So if you take an example of a limestone, because it's an easy example, limestone consists of calcium carbonate. So of course, the balance of this material is carbonate, and of course, carbonate cannot be measured by XRF. So we complement this kind of analysis with the balance of the material. So the balance of the material in this case would be like a loss on ignition. So a loss on ignition would be the portion of the carbonate of the material. Or if you don't have this kind of facility in your lab to do a heat treatment and gravimetric analysis, we could also complement this balance by estimating the balance, by measuring like a Compton line. So the Compton line is directly related to the matrix of the sample. And this could also be a way of determining your balance of your material. Yeah. There are other examples of balance, but that was the one for minerals. Yeah. But yes. Yes.
Yes. Thank you. And I think there are many more questions in the Q&A window. But I guess we wrap it up here. And thank you to everyone who attended. And asked a question, we will come back to everybody via email to which questions we haven't answered here live. And maybe a quick reminder for the survey, it would really help if you take the time and give us a small feedback.
Thank you. Thanks,
Thank you very much.
Okay, have a wonderful day, everybody.
Yeah, and of course, thank you to you, Cam, for the wonderful presentation.
Pleasure.